Okay, today we're going to talk about equilibrium and elasticity. Basically, we're going to talk about equilibrium. How does something stay put in one single place? This is also the topic known as statics in engineering. And you may be aware there is a statics course offered over in the engineering department with Beth Chung. Um, it's a very important topic that's essential to many fields of engineering, including mechanical engineering, and construction management. And in some sense, all the principles on which that entire course is based will be taught in this chapter. Now, that's not meant to say anything to lessen the importance of that course. They certainly go into much more detail and many more techniques to solve problems, and much more complicated problems. But the ideas behind it we'll be discussing here. Okay, so first off, let's talk about equilibrium. Equilibrium is when something is not accelerating translationally or rotationally, which means we have no acceleration, no translational acceleration of any kind, and we have no angular acceleration of any kind. Very often, we will be talking about static equilibrium, and the difference is with static equilibrium, the velocity is also zero, as is the angular velocity. So to be in equilibrium, we only need the acceleration and angular acceleration to be zero. To be in static equilibrium, the velocity and angular velocity are also zero. Now let's talk about a couple of different kinds of equilibrium, and then we'll talk about ways to solve equilibrium problems. The main Alright, we just talked about static equilibrium, which is when we're in equilibrium and not moving. The other three classifications of equilibrium, they're still examples of static equilibrium, but we want to know whether the equilibrium is stable, unstable, or neutral. A stable equilibrium means that if we move a little bit to the right or left, or if we move away from our equilibrium position slightly, we experience a force back towards the equilibrium. We talked about this a very little when we were talking about potential energy curves. So we see a potential energy curve here. In a stable equilibrium, you're at the bottom. It's flat and you're at the bottom of the potential energy curve that curves upward. That way, if you move a little bit to the side, you've raised your potential energy. The slope is positive, suggesting that we get a force back towards where we started. If we go the other way, here I've got a negative slope, which suggests a force back towards the equilibrium. If I take this square and tilt it right, it tends to fall back down to flat. If I tilt it left, it tends to fall back down to flat. At the opposite end is what we call an unstable equilibrium. In an unstable equilibrium, it's like being at the top of a hill. If we experience a slight force or a slight displacement to the right or left, then we'll experience a force further away from the equilibrium point. So here, if I were to move to this point, it would tend to roll all the way down. Slope here is negative, applying a force to the right away from the equilibrium. If we look at this block here, sure, it could be balanced on the corner, but if it tilts just a little to the right or just a little to the left, it's going to fall down onto one of the two sides. A neutral equilibrium is one where if we displace it a little bit to the right or a little bit to the left, we're still in equilibrium. There is no force pushing it back or pushing it away. So this example of a spherical object on a flat surface, I could turn it or move it left or right, and it would still be just as balanced or just as unbalanced as it was before. So it's neutral. Any position along here would be an equilibrium point. And this is represented by a continuously flat section of a potential energy curve.